Section 2.6 in our calculus class is entitled Limits at Infinity, Horizontal Asymptotes. Hopefully these limits at infinity help me find horizontal asymptotes, or horizontal asymptotes might help us find limits at infinity. So they're going to go hand in hand. So suppose I have this function, f of x equals x squared minus 1 over x squared plus 1. And I'm wanting just to know the behavior of this graph as x gets large. I'm going to go back to my fallback, the f of x table. And I noticed that it's an even function. And so that means that if I put in 1 or negative 1, it gives me the same value of 0. Okay, let's get a little bit bigger. If I put in 10 or negative 10, I get 0.9802. Okay, well, quickly that went to a nice number. Let's see if it continues to get closer to that nice number. If I put in 100, sure enough, yeah, I get 0.9998. And if I put in 1,000, add another 0 to it, I think I get an extra 9 in there, 0.9999. So I feel really good about getting a definition of a horizontal asymptote in this case. Because as x gets really large, my y value is getting closer and closer to 1. So what the graph of this would look like should look something like this. This is the graph of the function. And as you can see, as x gets larger and larger and larger, this value right here gets closer and closer to this red line. Okay? This red line is known as a horizontal asymptote. Horizontal asymptote. Okay. I think I'm ready to formally introduce this idea now. So if I let f be a function defined on some interval from a to infinity, then if I'm able to take the limit as x approaches infinity of the function, and it equals L, that means that I'm having values of f of x can be made arbitrarily close to L by taking x sufficiently large. Okay? So that is my definition of a limit at infinity. It's a little bit different because this time x is going to infinity, and I'm not getting infinity over here like we did in an earlier section. Now, this also works the other way. I can take the limit as x approaches negative infinity. Okay. If I'm able to do this, and I get a limit to exist, this is also called a limit at infinity. It just happens to be negative infinity. If you want to call it a limit at negative infinity, go for it. Get on board with that. But anytime you get one of these to be true, what you're going to get is you're going to end up with something called a horizontal asymptote. And notice that this L right here is just stemming from these limits that I have already found. And so I'm going to end up with a horizontal asymptote if either of these is true. I'm not going to rewrite it. If this is true, I'm going to be good. It's going to be a horizontal asymptote. Or if I take the limit as x approaches positive infinity, that's going to be true as well for a horizontal asymptote. Okay? So I want to look at some functions that have a horizontal asymptote. Tangent inverse of x. So the tangent inverse of x is going to act a lot like tangent of x, except that it's going to be lying down. Okay, and so tangent inverse of x has a horizontal asymptote at both pi over 2 and negative pi over 2. That's from a previous video. Let's see how accurate I can get on this. It's like 1.57 and negative 1.57. Okay. And so I end up with this line, like so. And again, what you notice is as x increases, I keep going up to 10, 11, 12, 100, I'm ideally going to get closer and closer to this dotted line, but never cross it. Okay, I'm allowed to cross it, but this one doesn't. Instead, what the end of these graphs are doing is it's modeling the behavior of the graph as x increases or decreases without bound. Alright, let's make one up. I should have already made one up, but We can make one up. Let's see. I want do this there, and then we'll go up, do this again, and let's come down. That's right. Obviously, I just made that up. Okay, so let's do a couple limits on this, and just looking at it visually. First up, let's do the limit as x approaches 4. The limit as x approaches 4. I'm not being real specific on this, but yeah, as I approach 4, from either the left or the right, I'm definitely going up to infinity. So whatever this function is, my limit would be infinity, which does not exist. All right, let's do another one. Let's approach 2 from the left. Okay, 2 from the left. I'm coming in to 2. I'm sorry, I have to do negative 2 from the left. Negative 2 from the left. I'm coming into negative 2 from this left side. As you can see, yeah, it's going to go up to infinity as well. Okay. Let's try negative 2 from the right. And when this x approaches negative 2 from the right, alright, looks like it's just going down. It's decreasing without that. Okay. We've done all this before. We've done infinite limits, where the answer is infinity. What's new today is the fact that I'm going to be looking for the limit as x goes to negative infinity of the function, and the limit as x goes to positive infinity of the function. There's a difference. We've got to be able to discern that difference, know the difference between the two. Okay, so let's do the limit as x approaches negative infinity. So that's just as my graph, as my function exits the sides of the graph, what value am I getting close to? Well, as I go off the left side towards negative infinity, my value is getting close to negative 1. And so doing the same idea with positive infinity, it's just going to be what my graph is getting close to as I exit the right side of the graph. I might have dipped down a little bit too far, but I tried to hit negative 3 right there. And what that means is both y equals negative 1 and y equals negative 3 are going to be horizontal asymptotes, which I like to call HAs. So I'm going to let you find these limits. Make yourself a table if you need to. If you don't need to, don't make a table. Just go ahead and fill in what you think these limits are going to be. So go ahead and hit pause, and then we'll come back and see if we got the same limits. I tried mine without a table. I thought about it, if x was really large, if x was like 1 million, 1 divided by 1 million would be something incredibly small. If I have 1/1,000,000th of something, I have a piece of that something that is so close to 0, it's ridiculous. Right? And it's the same way if x is approaching negative infinity. You think, well, you don't have a negative in there, but like 1 divided by something just incredibly small. Yeah, it's on the negative side, but we're still just so close to 0. And 0 is neither positive nor negative, so my limit in both of these cases would be 0. And this is very handy because this is actually going to give me a shortcut for evaluating a lot of limits at infinity. I should have a theorem coming up on that. I don't know if I'm going to do another example. First of all, I want to make sure you know that all limit laws for limits at infinity hold true. The same, I think there was like 11, 12, maybe 13 limit laws that we had back in 2.2. Those all hold true for whenever x is approaching infinity and negative infinity. However, I've got a couple to add. We've got an unnamed theorem here. We'll name this in class, but theorem 5, if r is greater than 0, if r is greater than 0 and it's a rational number, then I can take the limit as x approaches infinity of 1 over that x to the r will always be 0. What does that mean? Well, we just did it a while ago in the last example. We just took 1 over x to the first power, and hopefully you guys told me it was 0. I'm here to say it doesn't matter what this power is, as long as r is greater than 0, so we're not dealing with any negative exponents, you should get 0 every time. Okay? So if r is greater than 0 is a rational number such that x of r is defined for all x, then I can also work this in the negative direction. When there's x approaches negative infinity of 1 over x to the r would also equal 0. So that's what we illustrated in the last example. How is that going to help me with the tougher one? Well, let's look at a tougher one. Now, the direct substitution, continuity rules, they still apply to here, but if x is approaching infinity, it's really hard to get our hands on what's going on out there. Okay, so just imagine plugging in infinity to this. We're going to get something that is just really large on top, and we're going to, large, it looks weird just putting a negative sign. And we're going to get something that's really large on the bottom. They both get really large. So, if I'm dealing with a rational function, in order to deal with the fact that I have it pretty much infinity over infinity, or something just really large divided by really large, what I can do is I can divide everything by the highest power that I see in the denominator. Well, in that case, that's going to be x squared. Okay? So I'm going to write this out the long way, way over teaching this. But what that means is I'm going to take my numerator, I'm going to divide it all by x squared. I'm going to take my denominator, I'm going to divide all of it by x squared. So I just pretty much divided by 1 there, because I did it on top and bottom. It doesn't change the value of the limit at all. But again, I chose x squared because the highest power down here is an x squared. So if I do that, that's going to end me up with the limit, again, as x approaches infinity. This is just a common denominator. It's going to go with all 3 of these. So if I simplify each one, 3x squared divided by x squared is just 3. X divided by x squared. Oh, what happened? A little malfunction there. Alright, I'll catch it back up. Alright, so we said that was 3. And then x divided by x squared, let's see if I get it right this time, 1 over x, and then 2 over x squared. Well, those don't have any, didn't have a variable on that too, so I just have to write it as 2 over x squared. And using very similar math, I can simplify all of this bottom right here, using the same idea. Now here's a step I'm just going to show you once. I'm not going to be putting this in here every time. I'm going to change colors on it, so you see that this is probably only going to be in here 1 time. Okay? So remember, if I take the limit of all this, the limit of the sum and the difference and the quotient is the quotient of the limits. And so if I want to, this limit right here can go with each individual term that is in this rational function. So, as I write this, you can see why I don't want to do this every time. I'm going to write this limit over and over and over again. But what I've done now is I've set up that last theorem 5 that we just had, where all my limit laws are still intact. Okay? So for instance, if I take the limit as x approaches infinity of 3, then the limit as x approaches, doesn't matter what, if it's infinity, if it's 0, if it's negative 10, is always going to be that constant, because it's always that same value, that 3. Well, this follows my theorem 5 on the last slide. We already did this limit as x approaches infinity of 1 over x. We said it went to 0. Subtracting off 0. Well, imagine having 2 over x squared. 2 over something just incredibly large squared. You still got such a small piece of that it is going to 0 as well. So I think you see what's happening here. I get 5 there. 4 divided by something just incredibly large. You're still going to have next to nothing of it. Right? It's still going to be 0. Same thing here. 1 over x squared. It's going to be 0. So I get my limit as x approaches infinity of this to be 3/5. And I use my properties of limits to show each stage of this. So if the directions do ask for that, you need to go ahead and use it like it's a proof, like you're showing me every single limit law. It's a very long problem, but you do get a good answer at the end most of the time. You can definitely look at the graph of that later if we need to, but I want to do one that's a little bit harder. They sprinkled some of these in there on your practice. But it has these square roots on here. And it's going to ask me to find the vertical and horizontal asymptotes. If you're looking for a good halfway mark on this, I would probably do it around this problem. Right? So this is normally where we cut off, depending on how much time we have. But I'm going to go ahead and find the horizontal asymptotes first. We'll call it my odds. And so in order to do this, I'm going to take the limit as x approaches infinity. That's going to be my new way of finding horizontal asymptotes. So that whole little trick I showed you last year in pre-calc, it's done. I want to use the limits to find it this year. So I'm taking the limit, let's see, 2x squared plus 1 over 3x minus 5. Okay, let's use that rule. I have to divide everything by the highest power that's in the numerator. The denominator. So that means I have to take this whole square root, let's get the limit out here, this whole square root, I'm going to divide it by x, and I'm going to take the 3x minus 5, and I'm going to divide it by x. Well, algebra is not too kind to me when it comes to trying to take, when I'm trying to do this math right here, because the fact that this x down here is not underneath the square root makes it so it's really hard to combine. So what I'm going to do is I'm going to write something equivalent and use the fact that x is approaching positive infinity. I can change that to the square root of x squared, which does just give me x. That's going to allow that to combine a little bit better. On bottom down here, if I divide both of those by x, I get 3 over 5 minus x. So I'll go ahead and do that math for us real quick. And so now, taking the limit as x approaches infinity, let's see, if I divide, now I can divide each of these by the square root of x squared. And what that will look like is 2x squared over x squared plus 1 over x squared. And all that's underneath the square root. Now, like I said, I'm not going to take that limit like I did on the last one. I'm not going to take the limit of each individual term. Okay? Instead, what I'm going to do is just imagine if I have 2x squared over x squared, I'm just left with the square root of 2 right there. And if x is approaching infinity, 1 divided by something really large squared, I still got that little bitty part of it. Really close, so close, I'm just going to go ahead and call it 0. The limit as x approaches infinity of 3 is just going to be 3. And this 5 over infinity, 5 divided by something just incredibly large, is going to be 0. So that would go to 0. So I have a horizontal asymptote. This square root of 2 over 3 will be a Hahn. Now I need to check it to make sure it doesn't have another horizontal asymptote. That's right, I gotta actually plug in negative infinity on this one, just to check it. Just rather be sure on this. And so you're looking at a lot of the same math that we just did. Right? I'm gonna divide everything by x. And so on bottom, I'm just gonna bring this down. When I divide the bottom by x, not much change there. But watch what happens whenever I divide by x on this side. Okay. If I divide by x on top right here, I've got this square root of 2x squared plus 1. But whenever I do this square root of x squared, if x is approaching negative infinity, then the square root of x squared looks a lot like the absolute value of x. And if x is negative, that takes on the piece that has a negative in front of that x, meaning that this will have to have a negative. That's really weird how that works, but it all goes back to my piecewise function that defines my absolute value function of x. Okay, so what will that do now? Well, don't have me running my other problems, so I'm going to come down here, taking a limit. So I've got negative in front of this now. And so I'm going to, my square root of x squared, and I'm going to put it in there. All over, I'm going to do all my limit in one step. So again, I've got everything the same going to 0. The only difference this time is I'm going to have a negative in front of that square root of 2 that I didn't have earlier. And so this as well will be a ha. Now I know you're thinking, hopefully he forgets about the vertical asymptotes that the question asked about, because this has been an insanely long problem. I have not forgot about it. And I want to use my new definition of vertical asymptotes, the one that involves infinities. And so I see something critical is happening right here at x equals 5/3. And to show that it's a vertical asymptote, that is where the vertical asymptote is. I know that. But eventually I'm going to be wanting to graph this, and if I can do my limits with it, it's going to help with the graph. And so I can do the limit as x approaches 5/3 from the right of this function. And I can do the limit as x approaches 5/3 from the left of this function. And so on top right here, if I plug in 5/3, I'm squaring something, multiplying by 2, adding 1, it has to be a positive number. I don't know what the positive number is. I don't need to know what the positive number is. What I'm looking at, though, is whenever I plug in something close to 5/3 from the right on the bottom. Because 5/3 times 3 gives me 5. So if I approach 5/3 from the right, it's going to give me a little bit more than 5. A little bit more than 5 minus 5 is still positive. I'm going to say positive small. Positive divided by positive small is going to be infinity. Talked about that in an earlier video. If we need to make a table there, we definitely can. Not really any good dividing out techniques on it. So again, anytime I square something, multiply by 2 and add 1, it has to be positive. This time if I approach 5/3 from the left and plug it in, 5/3 times 3 is going to give me 5, a little less than 5. So imagine having like 4.99999 minus 5. So I end up with a negative value that's really small in this case. A positive divided by a negative number that's really close to 0 will give me negative infinity on this one. So that just verifies that this will be a vertical asymptote. That might be enough asymptote talk for now. Try to get through some of those homework problems, and we can work some more if we need to. Yeah, let's go on with this one. The limit is x approaches infinity of this. Wow. Well, I'm looking at this as two terms. If I take infinity and square it, add 1, and then subtract infinity, I have something really large minus something really large. Well, a lot of times that's going to give me 0 if I take something really large divided by something really large. Sometimes it'll give me infinity. Excuse me. Sometimes it'll give me a different number. And we're going to see that whenever we work on limits later on. But let's work this one. I really like my trick of dividing by the highest power in the denominator. Fortunately, there's not any powers in the denominator on this one, so I'm going to force it to have a power in the denominator. I'm looking at this, I see a conjugate. And the reason I see a conjugate is twofold. First up, it's going to give me a denominator. I like that. Now I have something to divide by. And it's going to clean up my numerator, that nasty square root of something minus x. So, whenever I multiply this, it's going to give me x squared plus 1. My O and my I cancel whenever I do all this foiling back and forth. And then my last term, negative x times positive x, negative x squared. On the bottom down here, we have 1 times this. Really my rule for this is just say no. When it comes to simplifying the bottom, just say no. Okay? Good stuff will happen if we don't simplify that bottom. I feel confident in it. So I get some stuff to cancel. That's nice. That went away. So I just have the limit as x approaches infinity of 1 over the square root of x squared plus 1 plus x. Again, the highest power in the denominator is kind of tricky on this one. We have x to the first here, we have x to the second, but that x to the second is underneath that weird square root. So, I'm just going to call it x again. I'm going to divide everything by x here and here. And so, what that will do, switch colors again, it's going to give me the limit as x approaches infinity of 1 over x. Well, we know what that's going to do. Remember, in order to go in here, since x is approaching positive infinity, I'm going to divide by the square root of x squared. While this x over x right here will just become plus 1. Anything divided by itself here as well. So keep in mind that x goes to infinity, and maybe I need another step in here. X approaches infinity. I have 1 over x, and inside that square root, I've got x squared over x squared. I'm going to call that 1. And I have 1 over x squared. So if x is approaching infinity, 1 divided by something really large goes to 0. And that makes me feel good about the answer being 0, as long as the denominator doesn't go to 0. And that cannot happen. Well, luckily, the only thing that's going to go to 0 is this 1 over x squared on bottom. I get 1 plus 1 is 2. Sure enough, the limit on this one did turn out to be 0. So if it's a difference like that, my goal is to change it to a function, a rational function that I can use that divide by the highest power of the denominator. Let's try this composite function. Not really a rational function. I can't go off and just start dividing everything by x. Arctan cannot be divided by x. That doesn't make sense. Okay? So I'm going to try to turn this into something that looks a little bit better. What I'm going to do on this, I'm going to use something called a t substitution, where I'm going to let t be whatever my inside function is. In this case, 1 over x minus 2. Okay, now looking at this, imagine just taking the limit of this little bit as x approaches 2 from the right of 1 over x minus 2. So x approaches 2 from the right would be like plugging in 2.01 in for this x. I get 1 divided by something really small, making it so this blows up. Okay? So what I would say is, as x approaches 2 from the right, my whole function right here, t, approaches infinity. And what that will allow me to do is rewrite my limit now. I can take the limit now as t approaches infinity of just arctan t, because all this middle part right here is simply equal to t. When we graph this at the front of the video, arctan of t, as t goes to infinity, got closer and closer to pi over 2. And sure enough, that pi over 2 will work as the limit here and the limit of my original function. Let's do a t substitution on there. Took something that was kind of in the way and difficult to work with and just rewrote it with a different limit. I'm going to turn you loose on one in just a minute. I do want to talk about this one first, though. Limit as x approaches negative infinity of e to the x. There's no denominator, and then we just have the basic parent function of e to the x. So whenever I see one like this, first thing that comes to my mind is just that graph of e to the x. Where that horizontal asymptote is. Let me change color so you see it. That horizontal asymptote right across here. And so if x is getting smaller and smaller and smaller, it's decreasing without bound. As you can see, I'm getting closer and closer to 0. Okay. So with that in mind, I want you to do this composite function. Use that 1 over x. I want you to rewrite that using a t substitution and try to find this limit. Okay, and come back and you can see my work and see how it compares to yours. I got 0 on this one as well. Let's do some quick ones here. Again, not much going on. I just want you to kind of think about the idea of I want you to think of the idea of what the graph is doing as I go off the right hand or left hand side of the function. This time it's sine x. You guys have told me that sine x is just this wavy line that oscillates between -1 and +1. So think about what this is going to eventually get to as x gets closer and closer to infinity. What's the deck out here? It doesn't stop. It just goes -1 to +1 over and over and over again. So since it does not approach a unique number, we can safely say on that the limit does not exist. Well, what about x cubed? Again, there's no denominator on this one. Yeah, I guess the denominator is 1, so you can divide everything by x to the 0, which gives you right back to where you started. But again, think about the graph of this. The graph of this, x cubed, is a snake on a plane. So, as x goes off the right side of the graph, as x gets closer to infinity, look at this line. It's going up. Okay? It's going to infinity. And on the left side, as x is going off the left side of the graph, it's going down to -infinity. So this would just simply equal -infinity. Not too much to think about those. Feels like we just did that. Alright, let's do this one. One bad part about making these videos is I don't get to sit there and just watch your wheels spin on a problem like this one. I like putting this one up and getting some ideas of what's going on in your head. So taking the limit as x approaches infinity of x squared minus x. Again, plugging in infinity, you get something really large minus something really large. The last time we did that, we got 0 for an answer. Well, it seems like if I was to plug in infinity and square it, I get something just off the charts large versus something that's just large, meaning that I would still have a very large answer. That's not very mathematical. Okay, I want to have it make sense to you a little bit more. So something I can look at doing on this is rewriting my function in any algebra method I could think of. And this way I'm looking at it, they both have a common factor of x. Now let's look at plugging in infinity. Okay, I got something large, and I'm multiplying it, growing rapidly, by something that's really large minus 1. Well, something really large times something else really large minus 1 is still going to be really large. All right? Though that limit does not exist, since infinity is not an actual number. I'm going to let you try this one. This one goes back to kind of the middle of the video. You kind of see we have an X in there, and so you can divide by that highest power that you see in the denominator and see what happens with this one. Alright, here's where I got to so far. Divided everything by X. Something unique happened here. Not everything went to 0 or a constant. So if I think about plugging infinity for X, I'm taking infinity, adding 1 to it. Alright, really big. Something really big divided by 0 minus 1 gave me a negative 1. I should be looking at negative infinity for that answer. Yep. Ooh, I like this one. I think I have this one in my notes, but we're going to go ahead and work it. It wants me to sketch this graph by finding its intercepts and its limits as X approaches infinity and negative infinity. I do have it in here, it's just kind of X'd out with it. I'll work it anyway though. Okay, so first of all, finding its intercepts. Well, whenever I'm finding the intercepts of a polynomial function like this, it's already factored. My x-intercepts are just going to be whatever makes all of these gems up here equal to 0. What makes each factor equal to 0. And so that tells me where it crosses the x-axis. So 2, 1, and negative 1. Okay. Now, let's see, by finding its intercepts. Well, I can find its y-intercept as well. I'm going to use the old trick of finding a y-intercept. I just got to plug in 0 in for all these x's. So that'd be negative 2 to the 4th, 16. 1 to the 3rd, well, that's 1. Negative 1, so negative 16. Maybe I should have counted by 2's on there. Here's what I'm going to do. I'm going to use my algebra 2 rule. Just if it's off the graph, just put it down there at the bottom. Next up, I'm going to do its limit as x approaches infinity. I'm not going to write all that out. And as x approaches negative infinity. Not writing all that out. Imagine plugging in infinity. Infinity minus 2 to the 4th. Well, that's going to be large positive, okay? And then imagine taking infinity and plugging it in here. Infinity plus 1 to the 3rd. That would be a large positive. Okay, and then plugging in infinity minus 1. That is a large positive. Guys, if I take 3 large positive numbers and multiply them together, it's going to give me infinity. Which means that after I cross this x-axis for the last time, as I go off the right side of the graph, this thing's going to be taken off quick and in a hurry. And let's do x approaches negative infinity. That's going to be a little bit different. Negative infinity minus 2. Okay. So imagine plugging in negative infinity right here. It's tracking 2 off, so man, I'm just so deep in the negatives right now. But I'm taking 4 negative numbers and multiplying them all together. Well, that's going to give me a large positive. Okay, can't even read that number. It's me. So I think it's a 3. Okay, imagine plugging in negative infinity right here. Negative infinity plus 1, I still got a really small negative number. If it's raised to the 3rd power, it preserves the sign, and I end up with a large negative number. Large negative meaning far away from 0, right? Deep into the negatives. And then infinity minus 1, that would be a large negative number. Okay? Well, 2 negatives make a positive. Positive times a positive is a positive. Yeah, this one's going to go to infinity as well. So we graphed something similar to this last year. We kind of had to make more sense of it. Well, one way this thing's going to be true is if I come down here, grab that x-intercept, come up. Oh, what in the world happened there? Let's act like that didn't happen. I had to actually go down that far, I was in trouble. And then I've got this 2 right here. Oh, from 1 to 2. Is that going to be a hill or a valley? Let's see, that's the F. 1. That 1 right there, I've got an odd multiplicity, so I always make it cross. So my graph is going to look something similar to this. This would be a rough sketch of it. Very rough sketch. That's the homework I'm assigning this year. Please make sure that this is the same homework that you are being assigned in Google Classroom. You guys have a fantastic day, and I will catch you next time.